It is my pleasure to introduce Scott Page. Scott is the Leonid Horowitz Collegiate Professor of Complex Systems, Political Science, and Economics, and maybe some other things too, I'm not sure. He was recently the director of the Center for the Study of Complex Systems at the University of Michigan. In 2011, by the way, he was elected to the American Academy of Arts and Sciences, and he has been for some time now an external faculty member of the Santa Fe Institute. Scott got his BA in mathematics at the University of Michigan, so he's an alum formally. His MA in mathematics at Wisconsin, and then he got a MS and a PhD in economics, decision sciences, economics and decision science at Northwestern University. He's had a variety of academic positions. He was at Caltech for a while, then University of Iowa, and finally came to the U of M in 2000, and he's been here ever since. He's the author of several books, one of which has been sort of central to much of my thinking about diversity, and that's Diversity, How the Powers of Diversity Create Better. I can't read my handwriting here, but it's really good. It's a really good book. Not only is it a really good book, but you can always tell it's a really good book because the New York Times said, in the beginning, in the long-running debate on affirmative action, Scott E. Page is a fresh voice. In his recently published work, he uses mathematical modeling and case studies to show how variety in staffing produce organizational strength. And nothing can say it better than the New York Times. So let's welcome Scott Page.
John and I really were joined at the hip there, which was great. Okay. What I want to do is I'm going to talk about modeling diversity. So my background is I'm trained as a mathematician, a game theorist, and modeler. And I was sort of a mainstream economist and then started hanging out with people who do complex systems work. And so what I want to do is I want to talk about some work of my own, but work by really a large body of people across a variety of disciplines who've been trying to understand what functional roles does diversity play. But before I start, I want to first mention Catherine Phillips, who's a very good friend of mine and sort of the yin to my yang. We've been talking about these issues the last decade. She's the Nancy Cantor lecturer. And she recently published a piece in Scientific American, sort of a survey piece where it says, there's decades of research by organizational scientists which show that identity-diverse groups tend to be better at sort of coming up with innovative solutions to problems. Now, if you fully flesh this out, what she'll say, and she and I've talked a lot about this, is that diverse groups tend to be the very best and the very worst. And so one of the reasons why we want to have sort of mathematical or mechanical or logical understandings of how diversity functions is to maybe get rid of one tail of the distribution and spend more time in the other tail of the distribution. She goes on to say that it's not that surprising that differences in expertise and tools and framings would be useful. But what's surprising is that it works out in terms of social diversity. And so in this space of sort of how diversity functions, this is sort of what we're playing with. Now, when we think about identity diversity, and this is some work by a friend of mine, Omar Wasow, who's at Princeton, political scientist, we tend to think in terms of things like genes, neighborhood, power relations, name, identity, diet, social class, this sort of thing. A lot of these things, it's very hard to do science on because you can't do natural experiments. You can't sort of say, okay, now we're going to run this again, and this time, Scott, you're going to be Native American, right? You can't do that. Like, you can do gene knockout experiments and stuff. You can take a species out of the ecosystem, but you can't do standard sort of causal inference sort of things. So running things on identity is hard. It's also the case that these identity characteristics, the thing we typically think of, don't really have a mechanistic connection to the sort of outputs we're interested in. So when we think about cognitive diversity, we think in terms of things like tools, perspectives, experiences, aptitudes, this sort of stuff. And these are the levers on which we stand when we think about diverse groups being better. Now, the interesting thing, and this is the sort of the intersection that's been fun to contemplate, is there's all these parts of identity diversity, there's all these parts of cognitive diversity, then there's parts within cognitive diversity in terms of how we represent the world and how we go about trying to change it, think about it, make sense of it, what we call sort of algorithmic and representational, which is a subset of the cognitive, and these all intersect in interesting ways. So there's parts of representative and algorithmic diversity that have nothing to do really with identity or very little. There's parts that have a lot to do. There's parts of cognitive diversity that have nothing to do with identity diversity and parts that have a lot to do. So it's playing with these intersections and understanding how they work in any given problem is sort of where the action is. So what I want to do today is I want to talk first, I want to sort of lay out a big sort of Richard Levin's big think philosophy of science argument about many models. And unfortunately, Richard just left us for a better place just a couple weeks ago. And then I want to talk about three particular cases: prediction, problem solving, and inclusion. And each one of these is going to have a very different sort of mathematical or sort of ontological structure, and that is the following. In prediction, it's going to be based on an identity. We're just going to have like a Pythagorean theorem, and it's just going to be like an algebraic fact that diversity is better. I mean, it's kind of like, you know, leg squared plus leg squared equals hypotenuse squared. In problem solving, what we're going to have is sort of like a Noah's Ark of models, a lot of it in response to my book, The Difference, where we got sort of some with strange results Liu Hong and I did about diversity being better than ability, and then a whole bunch of really smart people went out to prove us wrong and unfortunately proved us right, okay, which is interesting. It seems like prove us right, but they sort of proved the same thing in different ways. Then I want to talk a little bit about sort of, it used to be 10 years ago people talked about diversity, now people talk about diversity and inclusion, and I want to talk about sort of what we mean by inclusion, why it's useful in sort of a more mechanistic framework, and then I'll lay out some quick facts. Okay, so let's talk about why we model. If you rearrange these first letters, you get the word plead, so I'll be pleading for why we model. We do so to sort of get the logic right, to explain things, to predict, in order to inform actions, to design things, and to sort of just explore. Sometimes we write models just to explore, okay? But models, this is Picasso's model of the bull. Notice the relative size of the brain and another body part in this, and then let it go. I'll just name it. Models are simplifications, right? So as a result, as George Box famously said, with his hand on his chin, all models are wrong, right? Models, because they're simplifications, have to be wrong. But one of the ways we get around that is when we look at any sort of phenomena, whether it's something in the ecological system, whether it's something in economics or political science, we tend to have lots of models or frameworks we apply to it in order to make sense of it. And we get to what Richard Levins famously said, that the truth lies at the intersection of our independent lies, right? So every model's wrong, it's kind of a lie, but we can hope to get to the truth by having many of them, right, a diversity of models, and the truth is going to be at the intersection. Now the important thing here, Levins is a smart guy, or was a smart guy, and is that he uses the word independent, and that's crucial. Correlated lies are still lies, right? Independent lies get you to the truth, and that's fundamentally important. So this isn't just him spouting off. This is a very careful scientific statement from someone who's thought deeply about the philosophy of science. So we're going to play that out in the context of prediction. We're going to see the importance of independent lies. So this is gross domestic unemployment, or this is civil unemployment and gross domestic product. And what you see is these things are all over the place, and they're really hard to predict. And economists are very good at predicting the economy when it doesn't change much, and really bad at predicting the economy when it changes well. And so one of the things we study is what makes for someone who's a good predictor. Now there's a book that came out about 10 years ago by a friend of mine, Jim Serwicki, called The Wisdom of Crowds. And in this book, he begins it with this famous story of the 1906 West of England Fat Stock and Poultry Exhibition. There's 787 people. They're guessing the weight of a steer, right? So here's all these people in the West of England guessing the weight of the steer. And they've all got these guesses. The steer weighs 1,198 pounds. The average is 1,197 pounds, which is amazing. And if you want to write a book that sells lots of copies, it's wonderful to have a story like this at the beginning, right? Now, because you have this narrative that people can understand and it makes sense. And you think, wow, if it ever comes up, we've got to guess the weight of a steer. Let's get a whole bunch of people, okay? What we'd like to do beyond these sort of narrative accounts of jelly bean jar contest and guessing the weight of a steer is understand what is going on. Why is the group being accurate? So you can do something. I'm going to show you 3 different sort of logical frameworks that explain the basis for diverse predictions being good and why diversity is so important. The first one's going to be something I call the diversity prediction theorem. Now I call it this because of the fact that there's actually 4 different people who formulated this, and they all got tenure in different departments in the mid-1970s. So this is pre-internet, so cut them some slack. But basically, someone in statistics, someone in finance, someone in computer science, someone in economics, all basically wrote the exact same theorem at the exact same time. And the theorem says this: crowd error equals average error minus diversity. Okay? Now when I say this is a theorem, a couple years ago Ohio State won the national championship in football, and they wore these bracelets that said like O equals E plus M, like output equals effort plus meaning or something. That is not a theorem, right? That is like not science. That's like, I don't know what that is. Maybe it works for a football team, but this is like a real theorem, okay? So what does this say? This is the truth, T theta, right? So this is some true value like the weight of this steer. This is the crowd's prediction, which is the average of everybody's guesses. So the crowd minus the truth squared, that's how far off the crowd is. This is person I minus the truth. You sum up all the people and you average them. So here's the really funny thing happening on the way to the forum, no pun intended, is that if you take a bunch of people and you have them make predictions, the crowd's error isn't equal to the average error of the people in the crowd. It's actually better. And if that weren't true, markets and democracies would be really lousy institutions. So my 2 academic homes, to the extent I know, one of the grad students said, what are you like an expert in? And I said, well, that's the funny thing. Nothing. Right? I really don't know much about anything other than like sigmas and deltas and stuff. So what's interesting here is that if it were the case that the crowds there were the same as like an average person in it, it really wouldn't make sense to have everybody vote. It really wouldn't make sense to have this giant stock market. You could just kind of pick like seven, you need 20 people for statistics. You could just pick 20 people, right? But it turns out the crowd is better than the average person in it, and the amount by which the crowd is better is the diversity of the opinions, so the SI minus C. So what this means, and the reason I say diversity, not variance, is because variance refers to random variables, and these are realizations of predictions. So these are differences in what people think based on different models, different frameworks, different experiences, different exemplars, different analogies, whatever they're coming from. The differences in these predictions come from some sort of internal differences inside the people. So how does this play out? Here's Galton's steer. Average guess is off by about 57 pounds. So the interesting thing here is they could have been within a pound because they all knew the weight of the steer, right? Or they could have all been like some sort of savants that just can guess the weight of a steer. They can look at a steer and know the weight, right? But in fact, they were no better than you or I would be. They were off by like 56, 57 pounds. But they happened to be incredibly diverse. Now, why were they diverse? This is probably just an anchoring and adjustment diversity, right? They probably knew the weight of their own steers, which they just brought to market, and they probably adjusted up and down from that. And that diversity is reflected in the crowd getting it right, okay? Now, the interesting thing about this, I teach this online course called Model Thinking. I get emails all the time, and it's a regular basis, which prevents me from answering Deborah's emails. And this is the reason, Deborah. And what happens is people will say, Scott, I hope you're sitting down, but we just ran a contest guessing the weight of jelly beans or some other thing, and I plugged it into that formula, and the formula works. And I send them back this really nice email that has a right triangle on it where one side is 12 and one side is 5 and the hypotenuse is 13. And I say, hope you're sitting down, but check this out. 5 squared plus 12 squared equals 13 squared again. The Pythagorean theorem, let's hope Pythagoras is laying down because it's working again. I mean, the point is, it's always going to be true. It's always true. It's a mathematical identity. The question is, the deep scientific question is, if you want to get a prediction right, there's 2 ways to do it. One is to have somebody or a group of people who all can figure it out, right? So small equals small minus small, right? So if they all figured out their difference is low. The other way is the Levin's way, right? The truth is the intersection of the independent laws. So let me show you just some data sort of for fun that involves undergraduates, professionals, and beer company employees. I don't know where they fit between. They're somewhere the intersection, the midpoint between undergraduates and professionals. Okay, so here is Michigan undergrads guessing the number of Swedish athletes at the last Winter Olympics. The actual number is 103. The class predicted on average 65. But here's the crowd. This is the difference, that 30-some squared. Here's the average prediction. So the point is not when you do these things, and I've done hundreds of these things, this is typically what they look like. The crowd is so much better than the average person, right? So here's the Michigan undergrads. Here's the beer company, right? They were within 10. And here's the professional students from INSEAD, right? They were off by 30, right? This is what they look like. And occasionally, you get stuff that looks like this. Here's the INSEAD students on the number of cars per 1,000 people in Latvia, right? The actual number is 319. The average for the class was 318.58, right? So it's a brilliant crowd. But individually, they didn't know anything, right? And what was going on is some part of the class thought the answer was like 5, and some part of the class thought the answer was like 800, and then there was sort of a range in between, and it just turned out, on average, the percentage of people that thought nobody has cars in Latvia was about 2/3 of the class, and 1/3 of the class thought probably everybody has cars, and so between them, even though everybody got it wrong, on average, the independent lies get them really, really close. Okay, so that's model 1. And that model worked fine until I started hanging out with, I don't know what to call them, but let's just call them ecologists. Okay, so I started hanging out with this guy who was in the Michigan Society of Fellows named Evan Economo. And Evan and I got talking, and we said, it's not about the number of people, it's about the number of models, right? So when you think of an ecosystem, it's not like the number of individual things, it's the number of species. If you think about a crowd, you can think of sort of cognitive models as being the equivalent of species. Well, we have these ways of measuring these things. So if I think of there being n models, there's some distribution across the models. So this is the probability of somebody using model 1, model 2, model 3, model n. If you're an ecologist like Evan, you can think of this as sort of like the total weight of the number of ants, the total number of weight of otters, and the total number of weight of people, or something like this. But here it's the probability somebody uses a model. What we want to know is what's the probability 2 people use the same model. So if I randomly pick John and I, or Deborah and I, what's the probability we pick the same model? Well, 40% of the people are choosing model 1. The probability the two of us use the same model is 40% times 40%. Right? And if two of us, and if model 2 has a probability of 30%, the probability we match on that is 30% times 30%. So why does this matter? This matters because 3 people got tenure for this model, right? If you take 1 over that probability of matching, that gives you, if you're in political science, something called the effective number of parties. Or if you're in economics, it's the effective number of firms. It's called the Herfindahl index. Or if you're in ecology or biology, it's called the effective number of species, or Simpson's index. So how does this work? Suppose that you had 3 models that each were being used a third of the time. Well, the probability match on the first one is a third squared. Second one's a third squared. Third one's a third squared. 3 times the third squared is 1/9. That's 1/3. Flip it. That's basically saying it's like there's 3 things. That makes sense, right? If I've got 3 things that are equally likely, that's like having 3 things. But if half the people are using one model and a quarter each using the other models, and I do the same simple equation, I get 2.66 back. So even though there's 3 things, the fact that there's more of them on this thing means that it's kind of like there's not really 3 things. So political scientists use this because, like, in the former Soviet Union, they used to claim we have a democracy. There's 2 parties. But like as Stuart could tell us in the back, right, one party would get like 98% of the vote, right? And so they get 98% of the vote. That's kind of what we call a DINO, right, a democracy in name only. And if you computed the effective number of parties, you'd get like 1.02, right? And so what you want is you want some notion of the effective number of parties. So it turns out the following's true. If I've got a whole bunch of people out there, n people, and they're all using these different models, and suppose they've got a variance or an error of v, each one of these models, then Evan and Lu Hong and I proved that the error for the crowd is how sort of on average how far off is each person divided by the effective number of models. So it's not the number of people. So everybody's up by 20% or 15%. You're not going to get independent lies unless people have independent models. And it turns out the appropriate statistic is actually the statistic we use in ecology or economics or political science. It's the effective number of types. And so it's not the number of models out there. So this is where it's not size. It actually is the diversity of ways people think about something that determine whether the crowd gets it right. Okay? So let's go one deeper, just because that's what I get paid to do. Let's do something called the categorical diversity theorem. And so here, I'm going to leverage a lot of work from computer science and psychology. And they basically work as follows. They basically think when we see the world, we bin it. So psychologists have this notion of lump to live, right? So like, I don't think deep of anything. I might say this is an Indian restaurant, or that is a truck, right? And as you get bigger and older and smarter, you start making finer and finer categories. Now, the interesting thing is, when we think of the link between identity diversity and these categories, it's informed by language and it's informed by experience. And so there's wonderful things like in different languages, this is an Inuit word that means the feeling of anticipation that leads you to keep looking outside to see if someone is coming, right? This is a way of sort of categorizing a set of experiences that may be different than how you might if you were raised in a different culture. So how do these, and here's another one, the feeling of being alone in the woods, which is, German has a lot of words like this, right? Things bump things together. But the point is, like, we categorize things how they work. So what we do in these models is you partition the set of possible instances into categories, make predictions for each category, and that's sort of how it works. So let's suppose we're trying to look at how much chloride there is in water. And there's a set of houses. Now, one of my hobbies is making really good graphics. And so you'll notice these are houses with wells, and these are houses that are hooked up to city water. And you all knew that, but I guess for those of you that weren't used to this style of graphics. So this is the data. And then on the data is how much chloride there is in the water. So my categorical model might be, look, there's well houses, and there's houses hooked up to city water. And that's how I'm going to construct my categorical model. And this is implicitly what you do whenever you run a regression, right? Whenever you sort of choose a set of variables, you're implicitly creating partitions, whether you like it or not. So there's a total variation in the data. There's a residual variation after I run my model, after I make predictions for the model. And then there's an R squared, which is how much of the data that I explained, right? This is like what we do in social science. Every day in ISR, there are people doing this. Even as we speak, people are probably doing this in ISR. You can think of this graphically as there's total variation here. And then you can say, once I create these categories, once I step off the bus and say, OK, here are categories, I'm sacrificing something. There's a categorization loss. So if I made the best possible prediction for each category, I'm still going to miss 10,000 of the variation, right? Just by binning. As soon as we bin, we've made errors. But it's also the case, even once I've binned it, my prediction might not be right. Right? I'm going to have what we call model errors. So you can think of there being categorization error and then model error. So this is just the error in my model. So if I do a lot of math, which is sort of fun to do, I find out my sort of prediction error, my modeler is 1,000, and I can do something like this. I can say there was 20,000 units of variation. I explained 9,000, which is my 45% R squared. I lost 50% just by making categories, and then there's 5% that I lost from the prediction error. Okay? So why does this matter? Because if I think about, we're trying to make sense of the world. There's total variation in the world we're trying to make sense of. The amount we explained, that exists of the amount we explained, plus the category loss, plus the predictive error. So if we have diverse categorization, so now we have people say things like, oh, you want people with different life experiences, you want people trained differently, you want people who sort of have different analogies or different narratives. That, in psychology, that's fairly easy to link to different categorizations of the world, right? Like the feeling of standing alone. And so when you sit in a meeting, it's rare that you like write down something mathematically and it changes how you behave in meetings. Okay, that's really rare. Let's just admit it. But this work actually fundamentally changed how I think in meetings, because if somebody said something that just didn't make sense to me in a meeting, I'd be like, okay, that is just a weird way to look at this, right? And I would like start singing Adele in my head or something, right? No, it's just like whatever. It just didn't seem that germane. But now I realize if somebody's categorizing the world differently than I am, that's like really good, right? And the reason it's really good is because they've got a diverse categorization, and so their categorization error is going to be different than my categorization error. And here's what's really funky, is that scientists, deep thinking computer scientists who study ensemble learning theory and stuff like that, they spend a lot of time thinking about how do we construct interesting diverse categorizations, right? And yet in the social realm, when people talk about everybody has a different perspective on this, that often is seen as a political statement, right? But it's actually kind of like a mathematical statement, right? That it's, you just do better if you have different categorizations. So let me give an example. This is a young scholar here at Michigan who seems to be doing quite well. He's got 147,000 citations, so that's he's probably doing okay. And no, he's an amazing biostatistician, Giancarlo, and he was involved in this project where you're basically doing, he's a biostatistician, you're basically trying to identify alleles. This is a funded research, and it was a competition between Michigan State, Harvard, and Michigan. And the higher you are, the worse you are. So this green line is Michigan State, which would be in third place out of 3 if you're keeping score at home, right? And then it's kind of a tight race between Michigan and Harvard, and it turns out Michigan wins, which is why he has 100,000 citations. So he's a little bit better, but these are really sophisticated models that rely on sophisticated techniques to bin things and make predictions about whether something's a gene. That's a simple way to think of it. Well, so they do these things, and then they announce the winner. They raise his hand. Everybody else is like, congratulations. And then the funding agent says, it's interesting. We've got 3 different models. Why don't we just have them vote? Let's pretend it's a democracy of biostatisticians. If you vote, that's this line. That's way better, right? And so we tend to think who's got the best model, but the thing is the best model is going to be the combination of diverse models, right? This is just kind of like a fact. And so what you want, and so the Michigan State model, which is the worst model here, if you look at it alone, could actually be the best model if it's the most diverse model, if it's the least correlated model, the other, if it's sort of using different techniques. So when you think about ensembles of people trying to predict, and again, I'm just in the prediction realm, what you want is you want diverse categorizations, right? Which is an interesting thing. So that's not a political statement, right? It's just kind of a mathematical fact. Okay, so let's stop that one, and now let's go to problem solving. So just you've probably got this sense, but I'll sort of drive it home more clearly here. So the point is people will say diversity good, diversity bad, that sort of stuff. What I'm trying to do is say the following, okay, what is the nature of the task? Are we predicting something? Are we solving a problem? Are we classifying something? Are we creating ideas? Right? What is it that we're doing? Then once we know what it is we're doing, then I want to say, what sort of things are people bringing, when they bring their whole self to the table? What are they bringing? How do those things differ? What are we calling ability in that context? What are we calling diversity in that context? And how do those things aggregate? Problem solving is super interesting for the following reason. I teach this modeling class, and I begin it by talking about one of my favorite websites, which is called the Opposite Proverbs page. The simple version of this page is everything your grandma told you, your grandpa said the opposite. So your grandma said, he who hesitates is lost. Your grandpa said, a stitch in time saves 9, right? Your grandpa said, 2 heads are better than 1. Your grandma said, too many cooks spoil the broth. Now, the reason that we model is that they're both right. There are cases where 2 heads are better than 1, and there are cases where too many cooks spoil the broth. And one of the reasons we write down formal models and one of the reasons we do empirical work is to figure out where that line is in that set. So here we're going to play this really fun game. And the game is I'm going to create like the set of all problems that people could try and solve. And then I want to ask the following question. When is it the case that you should best team of people consist of the best people? And when is it the case that the best team of people doesn't consist of the best people? Because I live in this weird place called America where we give people tests and then we think, oh, the very best people are the people who scored highest. And if you don't let the highest scoring people onto the team, you're discriminating against them. And if you let someone in who didn't score highly, then, you know, that's giving them an unfair advantage. But the reality is, if the best team doesn't consist of the best individual performers, that's not discrimination. That's choosing the best team. So the question is, what does the best team look like? Does it look like the best individual performers? So you set these models up as following. There's n agents. They've all got some ability that we have some way of measuring. And I want to find a team of people, and there's going to be some performance of the team. So analytically, it's a fairly simple thing. I just want to choose the best team. And so you might think, oh, this is what IQ tests and SAT tests and GRE tests are for, or prelims are for. We found who the highest ability people are, and we put them together. Well, if this were 1840 and we were hiring people to chop down trees, this would be exactly right, right? Because if I'm hiring people to chop down trees, and I'm going to hire 10 people, I should hire the 10 people who individually can chop down the most trees, right? Because total production is the sum of the number of trees chopped down. So if you can chop down 40 and I can chop down 30, you're better, right? But we're not chopping down many trees, right? The emerald ash borer now does it for us, right? So we can just sort of pick them up off the ground. So here's then the sort of interesting thing. You could say there's this ability mindset, which is pervasive in the United States, but even more pervasive in Singapore, I found as I spent some time there a couple years ago, that the best team should consist of the best individuals, right? And that makes a lot of sense. He who hesitates is lost. We could also say, no, maybe it's really about diversity. You should have diverse teams, that the best team does not consist of the best individuals. You actually want to search for diversity. And then you could say something really crazy, which is that diversity is so much better than ability that if you put in some bar for like basic competence, you're better off picking a random team than the team of the best. You know, that's insane, okay? But it turns out, here's what's really weird. This one, there's something that Liu Hong and I call the equivalence conjecture, which is, we could call a theorem, but it scares people too much. That if the best team doesn't consist of the best individuals, so if it's true that it's diversity over ability, then it turns out that it's also diversity trumps ability if you're picking from a big population, which is really weird, right? So basically, these two claims are sort of the same. So if it's the case that the best group isn't the best individuals, then it's also true that if you're picking from a big set and you put in some competence bar, that you're almost better off picking randomly than you are picking the best, okay? That's just sort of a mathematical fact. So here's the ability view. The ability view is there's a whole bunch of people out there and we can give them some tests and we can kind of measure the size of their heads or something. And like there's the best people and then there's these other people and the best team should consist of the best people. And let me give you the background of this because this is sort of like my most embarrassing teaching moments. I'm teaching at Caltech. My first year I'm teaching intro econ and I'm teaching, you know, standard John Taylor's book. And we're talking about ability models and how you get paid based on your ability. And the students are, let's just say, bored out of their living minds, right? And I say, so why are you bored? This is like economics. What's more exciting than economics? And they said, no, economics is fine, but like the models are like people putting rivets in planes. We're not going to put rivets in planes. We're going to be neuroscientists. And I'm like, it's a metaphor. You know, like, you know, rivets in planes are the same thing as like doing neuroscience. Like you just hire the best people doing neuroscience. And then I went home and I'm like, God, I wonder if that's true, right? Because like, you know, I was thinking there's an ability to do neuroscience, and I realized I was making this sort of implicit additivity assumption, right? Which doesn't make sense because you can't add up IQ. So if John's IQ is 140, and mine is, I took a lot of IQ tests, and my IQ hovers in this close range between 80 and 136. It's somewhere right in there. So let's just say it's at the lower end, 90. It's not like when we add me to John, we get someone of 230, right? No, we wish. So the thing is, then I thought, okay, well, let's construct the model. So I constructed a model, and this didn't work. Every time I picked a random team, they did better than the team of the best. And so I call this a green eggs and ham result in the sense it was true on a tree, it was true on a plane, it was true on a bus. No matter how I set it up, it was always true. So eventually, Liu Hong and I proved a theorem, and I'll get to that, but here's sort of the logic. And the logic is best expressed through a paper. Jonathan Bender, who's a professor at Stanford, said, you know, there's got to be a simpler way to do this. So the simple way to do this is this. You want to think of people as having sets of tools, right? And when I give somebody an IQ test, what we're doing is we're asking, do they have the right tool? Do they know which tool to apply to the problem? And do they apply it correctly? And if you do all those things the right way, right tool, know which one to apply, do it the right way, you get the answer right. If not, you get it wrong unless you're lucky, right? So IQ tests are in some sense a measure of how many tools you got and your fidelity of applying those tools. So we construct a very simple model that looks like that, and I'm going to draw that same picture before. The team of the best are all people who have quite a few tools, right, a lot of tools, and they have the appropriate tools. So I spend a lot of time talking about this stuff at like the Federal Reserve banks, and when I go there, it is like my people. It is like all people with PhDs in economics, masters in mathematics, right, some political economy, some know economic history, and some know game theory, right? So they're all, in my opinion, really smart people, super capable people, but we're all the same, right? So whenever possible, I trash the state of Illinois whenever I can. So who is the Illinois person here, right? So the IL person might be a physicist who studies networks. Now, is a physicist who studies networks good at solving an economic problem on her own? No, right? However, the IMF has 600 economists. Would I want to pull one of those 600 economists out and replace it with someone who knows a lot about networks? The answer is sort of unequivocally yes, right? So that's the logic. When you think about putting a group together, you're not adding up IQs. You're taking the union of tools, right? That's the simple logic in this model. So if you set up a tool-based model a la Bendor and Page, then what you get is that the diverse group is better. Now the original model, which is the Hong and Page model, is borrows from this guy, a young man named Sewell Wright. Some of you probably know, right? And he had this funky idea of there being these sort of things called rugged landscapes. So the Hong and Page model basically has this Zen-like moment in it where we say, there is no landscape. What do we mean by that? It's a beautiful thing to say. The reason we say there is no landscape is in biology, the landscape depends on the genes, right? This is Wright's idea. It's a simplification. But in a social problem, you decide how to represent it. So when someone says, Deborah and I have different perspectives, what that means is we've encoded things differently. And if we encode things differently, we have different landscapes. So it's a peak on my landscape might not be a peak on her landscape, right? And so this sort of the idea of diverse perspectives, which people think of in some sort of loose sense, if you interpret that as diverse mathematical encodings, you see that it has incredible power because like where one encoding gets stuck, another encoding might not. So it was funny, I was at NASA and I said, okay, if somebody says to you, I'm talking to a whole group of engineers, and I said, so somebody says to you, diverse perspectives are valuable. How many think this is kind of like some politically correct statement? And like nobody raises their hand. I'm like, okay, come on, I'll close my eyes. And then like every hand goes up. And I peeked, right? And then I said, okay, suppose I said to you next week you have to choose between polar coordinates or Cartesian coordinates. You can't use both. They're like, well, that would be totally impossible because sometimes I have to, if I'm doing planets, I've got to use polar coordinates, and if I'm doing other stuff, I've got to use Cartesian coordinates. I'm like, oh, diverse perspectives are valuable? They're like, okay, uncle, right, we give. Right, so the point is diverse representations are useful, but even within the same representation, different starting points, right, or different sort of heuristics lead to different local optima, right? And so collectively we're going to do better than each one. So diversity in how you search even the same landscape is useful. So this is the Hong Page result. Well, so this result is out there, and then people started saying, God, I wonder to what extent this is true, right, more generally. So John Kleinberg and one of his graduate students, and John is certified by the MacArthur Foundation as a genius, he said, let me think of this the way a genius would think about this. And he's a friend, so I'm only like half joking here. So and John says, let's think of, you know, when somebody looks at a problem, they get like some draw from a distribution, right? And the smarter you are, the further over your distribution is. So now if you do that, you've got to make a distinction between 4 types of problems. First are additive problems, which he's a computer scientist, he calls them additive, I call them chopping down trees. The second are best contests, where you can sort of say who is the best, right? So these are sometimes called conjunctive problems if you're a computer scientist. Then there's sort of multi-dimensional optimization problems that are hard. And then there's problems that have a lot of synergies and coordination. So what he shows is, on these classes of problems, there is something called ability. On easy problems, like who is smartest, or we add them up, then ability wins. And on anything hard, diversity wins, right? If you're in grad school, you know, guess what? They're all hard problems now, right? So in the world of simple things, ability makes sense. In the world of hard things, at least according to a genius, it's diversity. Okay, now the best paper in this whole thing is this one by my friend Professor Marcolini, who went to graduate school to prove me wrong. I mean, literally, I meet this guy, and he goes, I went to graduate school to prove you and Han wrong because that just had to be false. So what he did is he said, he goes, but it had to be false if you were doing something really complicated like playing Go. So his application to graduate school has said the following. I want to write a dissertation where I do the following. I'm going to create a bunch of algorithms that play Go. Then I'm going to take a team of the best algorithms and compare them to a team of random but good algorithms, and I'm going to prove Hong and Page wrong. It didn't work. The team of the worst algorithms did better, almost always, right? But the reason why was a very different reason. The reason why is Go is incredibly high dimensional, and if you have a whole bunch of algorithms that, and so sometimes you're going to probably make a mistake. If you've got a bunch of algorithms that are all similar to the best algorithm, they make the same mistake. If you've got 11 algorithms, he typically worked with 7. If you have 7 algorithms and it's a really hard thing, and so they're really likely to make a mistake, he used a simple voting rule. Well, if 2 of them choose the same action, the odds that they chose the same wrong thing is really, really low, right? Because mistakes are much more random than the correct thing. And so it gets back to Levin's independent lies logic, right? So there's 1,000 possible moves you can make in a configuration. If 2 very different algorithms choose the same one, it's probably the right one, right? And so the diversity in terms of errors actually drove the result. So it's sort of uncorrelated errors in gameplay. Then the last one, there's a recent paper by Alvaro Sandroni and Wilhelmina Ketz, and then this is Jenna Bednar, and I have a paper as well on this, that show you can also link this diversity to sort of exploration and just basic ideas of exploration and exploitation. So if a population of agents and the environment's changing, what you'll get is you get that the diverse group tends to do better. So basically what you come through from all these papers is if the task is easy, then the best team consists of the highest ability people, and that's proven in 3 different papers, right? Diversity over ability is if the problem solver is hard and no single tool solves it, that's what Bender and I show. If it's non-separable or additive, that's what Kleinberg show. If there's lots of peaks, that's what Hong and I show. If it's a big action space, that's what Marcolini shows. Or if the environment's changing, that's what Bednar, Ketz, and Sandroni show, then the best team will be diverse, right? And then what you can show in sort of all of these, if, that should say large instead of arg, if you're choosing from a really big population, if everybody's diverse and competent, so otherwise you get the sort of the monkeys on the typewriter phenomenon, and it's a hard problem, and you're picking a team that's moderately sized. Because if you're picking a team of 1 person, the team of the best is going to be better than a random person, right? But once you start getting to like 10, and that was the funny thing like with Go, he's like, in order to have the team of the best beat the team of random, he had to like have the teams be of size 1, right? Once the team gets to be of size 3, the random team is doing better. Right, so and in some of the stuff I've done with Lou, and Patrick, I could also put some wonderful work by Patrick Grimm up where he looked at several suites of problems, 7 to 20. But the interesting thing here, it becomes hard to do. This is the thing that Lou and I found, and everybody else who's been in this space has found. If you write down a mathematical model or a computational model where you create a huge set of problem solvers, and then you have some test where you choose the best ones, and then you choose some random selection of people who are good above some bar, it's really hard to make it so the team of the best wins. It's really hard. You've got to kind of like, it's like that joke about the sport coat where the person stood like this and it fits perfectly. And you've really, really got to like manipulate and maneuver and change it. So the thing is, the general feeling from 5 different studies, people from 5 different disciplines using 5 different types of models, is that kind of as a rule, when the problem gets hard, if you can pick from a lot of people, go diverse, right? It's not like it's a mathematical fact, right? This is, what are the conditions under ones it's true? And what really seems to drive it is when the problem gets hard. The harder it is, the bigger the benefit of diversity. Okay, so if the test is additive, then it works, and if not. Okay, so let me talk then quickly about inclusion, then I'll give some quick facts. So the diversity space, like in the 1960s, was just be diverse. And that failed miserably because we weren't inclusive. And I want to give sort of a really fun inclusion experiment that my undergrads and I figured out, which is this. It's the LSAT. So we're going to do the diversity version, the LSAT and inclusion. So the LSAT, they ask you questions like this. A panel of music historians ranked 8 contemporary songwriters, Jackson, King, Lennon, Mitchell, Nix, Prince, Simon, and Wonder, according to their impact on popular music. Okay? Then they give you a set of facts. Like Nix is ranked above Lennon and below Simon, Prince is ranked below Mitchell and Jackson, right? They give you a set of 5 things. So what we could do is define. So here's the experiment we can do. We won't do it enough time. You can take one person or one set of people and say, this is what you know. You know fact one, that Nix is ranked above Lenin and Simon. Then you take another person, another group, and say, this is what you know, fact two. And then another group knows fact three. And another group knows fact four. And another group knows fact five. Then you say, here's the question. If Simon was ranked fourth, which one of the following must be true? And then you ask those 5 people, and you know what they say? Person 1 says, I have no idea. Person 2 says, I have no idea. Person 3 says, I have no idea. Person 4 says, I have no idea. Person 5 says, no idea. The reason why is, if you solve this thing, here's the facts. It turns out what you have to do is, if Jackson's ranked above Simon, that means J is above S. If Nix is ranked above Lenin and Simon, that means that it goes Simon, Nix, Lenin somehow, right? 3, Wonder's ranked below Nix, so Wonder's got to be below Nix. And then 5 is Nix is better than King. So what that means is, from 4, we know that Jackson's above Simon. From 1, we know that Simon's above Nix and above Lenin. And we know that also that Wonder and whoever K was is there, right? And then we know Prince is ranked below M and J, right? So if Prince is ranked below M and J, the highest Prince can be is 3rd. Prince has to be 3rd, right? So why does this matter? The reason this matters is when we think about diverse groups solving problems or diverse groups coming to some sort of thing, it's not just the case that you can just sort of walk in and say what you know. Oftentimes you've got to combine that knowledge in a deep way. And if you don't combine that knowledge in a deep way, you may miss something, right? So the simple example my undergrads had was this. Here's 3 facts. Houses in Flint have lead pipes. Minerals corrode pipes releasing lead. Mineral levels vary by season. If you know all 3 of those things, you never would have allowed that to happen. But you'd have to know all 3 of those things and think through them, right? You have to know these are the seasonal variations in lead, right? So if you don't know the seasonal variation in lead thing and don't integrate that with the other stuff, you don't get to the right answer. So what's interesting about inclusion is it's not enough to just have the facts in the room. You've actually got to have the intersection among the facts. Okay, so some quick summary data, and then we're done. So when I wrote my book on the difference, when all of us were doing this modeling, in the interim there was all this work being done on sort of big science. And so it turns out, here's this interesting thing. This is from a study called The Science of Team Science by the National Research Council. From 1959 to 2013, the number of co-authored papers in social science went from 10 to 60%, and in science and engineering from 60 to 90%. And the 90% figure is a total underestimate, because the 10% of sole authored papers, something between like 60 and 90 some percent of those are survey papers. So actual research papers, who knows? But people put it between 95 and 98. So basically, no one's doing science alone, right? And in fact, the modal paper, there's more papers with 6 to 11 authors than there are with 1, right? A friend of mine, Josh Burke, landed a paper in a major journal. He only had 13 co-authors, and I said, imagine if you were friendlier, how good that paper could be, right? If you look at, this is the hardness thing. This is some work by my friend Jacob Foster, which is awesome. This is a log scale for chemistry. I figured, I'm in the chemistry building. I can now say I've lectured on chemistry in the chemistry building. If you count the number of diseases, chemicals, methods, and authors on a log scale from 1950 to 2010, they all kind of go up in a way, right? Which is interesting. Okay, so it's just become more complex. Now, why is this the case? If you look at the number of citations or the impact factor, and you look at the number of email addresses, references, or past papers, those all have a positive effect. So what does that mean? If you take people from different universities, holding everything else constant, you get more citations and more impact factors. But this is just a sample. This is just a small sample based on every paper ever published. I mean, so it's not a sample. It's not even clear what you, there's a question of like how you think of this as a regression, because it's like everything ever done, right? So it's every paper off the Web of Science. Now, homophily is a fancy word that social scientists use, like, are you from the same racial or ethnic group? So they coded the author's last names as to whether or not we're the same ethnic group, and that's negatively correlated. So the summary from this is, if you want to get a B+, co-author with people from your home school, from your same group, right? Now, why are people co-authoring, and why is all this team stuff? It turns out if you look at papers with more than 100 citations, which you probably do look at Google Scholar and think, I wish I wrote those, you'll see that you're 4.5 times as likely to get one if you're co-authored. That's why. The reason those curves are going up, it's sometimes like learning actually does work. Basic models from economics do work, right? Like you're 4.5 times as likely to write a home run paper if you work in a team as if you work by yourself, right? Even more interesting, this is my favorite graph from this. This is a smaller sample. It's only every paper in Northwestern's library. It's not like it's Michigan's library, right? I went to Northwestern, so I can say that. So it's a big library, but it's only the 13th biggest or something. Okay, but here's what's really cool. This is the bonus you get from co-authoring, holding everything else constant with someone from another university as a function of the tier of the university. So tier 1 universities are places like Michigan. Tier 2, as of last week, are places like Dartmouth, in case any of you graduate students were thinking of Dartmouth. Tier 4 universities, now, if you co-author with someone from a tier 4 institution, you do worse. They don't talk about that too much in the paper. Just kind of let that one go. So there's a sense in which you've really got to be working with really serious people trying to do research from the better the schools are, the more working with different people from different schools helps you. Okay. Now it turns out if you unpack this, they say it turns out to be atypical combinations. They have this really complicated way. I'm going to show you Melissa Schilling's way, which is better. Now this paper, though, I should say, sorry to go back and forth, looks at every paper. This has got that 2 million paper things. This is just a subsample of the good papers. But this is totally fascinating because this is an odds ratio. So an odds ratio bigger than 1 means it helps you. If you double the number of authors, the odds of writing a home run paper go down by 20%, which doesn't make any sense because I just told you it goes up by 4.5. But remember that sort of effective number of papers thing, effective number of species, probability of matching? That's this. This is the Herfinell index because she's an economist. If you double the number of disciplines you draw from, you're 3.5 times as likely. So welcome to the land of diversity. And this is the atypical combinations. If you cite literatures that have never been cited before together, it goes up by 15 times, right? So Melissa and I joke, this kind of like explains what marriage is like, right? It's a pain. It's kind of like 20% worse having to do something with somebody else all the time. But they were sort of no different stuff, right, that you can combine. And occasionally, like you put ideas together that make a lot of sense, right? And so it is not, you would rather, what this says, and it's really important, you'd rather have all the ideas inside the same head, right? I mean, you'd rather have it to be that, like, when Evan and I wrote those papers on effective number of models, it'd be better if I just could have, like, dumped all of my econ knowledge into Evan's head, or he could have dumped all of his biology models into my head, and I could have written the paper. I've gotten all the credit for it and everything else. But you can't do that because the pumpkin's only so big. That's still going to cost us, right? But the benefits outweigh the cost, and this is where the inclusion stuff comes in. Okay, 2 minutes left. Let me just stop there. Thank you for. Okay, so questions. If anybody has questions, nobody has any questions. Deborah, you must have a question. You could ask your email. The question you ask on email.
No, that's a boring question.
Okay, yeah, go ahead.
So you talked about studies that compared to computer algorithms.
Yeah.
So did people with different kind of approaches.
Right.
Are there any studies that looked at advantages of using people and different computer approaches to solve this problem from a person's stage?
Yeah, so there's a lot of, there's idiosyncratic stuff on like weather forecasting, chess playing, stuff like that, right? And as a general rule, people sort of say the best thing isn't formal models or people, but formal models and people, primarily because of the fact that, there's a lot of work on AI is very different than how, or it appears to be very different than how humans think. And so these same sort of models would explain sort of why you'd expect that to be true. Nate Silver in his book, The Signal and the Noise, talks a lot about how like the computer weather forecasts are just way better than people, but people using combinations of computer weather forecasts are actually better than the computer weather forecast. So but if you talk to, combining people with like if you give people a whole bunch of computer forecasts, they can combine them and do better than the forecast. The thing is, the strong AI people say eventually the AI is going to beat us. But the thing is, the AI is relying on diverse models, and they use ensembles of models. There's a wonderful piece in Science by Burke, I think it is, on weather forecasting just last year, and it's amazing how much better they've gotten. It's all being driven by just much higher granularity of data, but then and also using these suites of models. Yeah, Deborah.
So I'll ask the one that you started by talking about this, but I'm still not sure I really grasped it, which is that the tool idea is very clear. There's multiple tools. The connection between diverse tools and diverse social identities is the one that's, is that an assumption or is
So this is,
go past that?
So when we say diverse, so this is like, so when John and my model, we tried to make the starkest model possible, which is say it gets diverse tools, right? And that math is an analogy that works. But when you actually look at and that's why I did all the models of prediction. When you actually sort of really start digging down into prediction, what you see is that it's either diverse categorizations, right? Or it's sort of diverse models within the same categorization. If you look at problem solving like Lou and I did, it is this sort of like this, Zen Sewell Wright moment where you say sort of there is no landscape, right? In the sense that like there's many ways you can represent things. So an example I give to unpack that is when Ben and Jerry's came up with, this is in the book, but when Ben and Jerry's came up with New York Super Fudge Chunk ice cream, they got a big table, and on this axis they increased the number of chunks, and on this axis they increased the size of chunks, and this was like an ice cream landscape, right? The poet Ted Hughes actually has a poem where he talks about summits and ice cream landscapes, which is beautiful. But this is an ice cream landscape, and you can imagine like there's some pint that's got like the highest value, and they have professional tasters kind of like, actually they searched using what computer scientists would call von Neumann neighborhoods. So they went into a pint, and they went to the north, south, east, and west, and then they found a peak. But a consultant or like someone who like went to Weight Watchers or something might say, hey, let's take those same pints and line them up by calories. That's just a different way to think about ice cream, or line them up by butterfat. Well, what's a peak in their ice cream landscape might not be a peak in the butterfat or the calorie landscape. And so what you can say then is if representations do two things. Well, first we're just talking about prediction and problem solving. In the case of prediction, they create different categories, which leads to uncorrelated errors, which leads to the sort of Levin's like independent lies. In the problem solving context, they play a different role, and that is that if we have a different representation, we probably have, the global peak has to be a peak for both of us, but we probably have different local peaks. And so it's really, so where you get stuck, right, I may not get stuck. Maybe obvious. And so one of the things I think, one of my friends says this explains consultants, right? No, because because you work at Ford Motor Company for 40 years, and then you bring in someone from McKinsey, and they like point out something that you're doing wrong, and you're like, oh my gosh, that person's a genius. And they're like, no, I'm just thinking about it a little bit different, And they just basically took some idea they learned at Boeing, right, and apply it over here, right?
So again, but I still want to make sure I'm getting this
Yeah.
right. Whether you're talking about the diverse categorizations and the prediction problems,
Or the encodings, right?
The underlying assumption, which I think has to be true, but it is nevertheless an assumption, is that diverse social identities will have diverse categorizations or diverse representations or diverse tools, or like, that has to be part of this, right?
There's two things, and so if you read, and Catherine will talk about this, I hope, during her talk. So there's two things about this that are really interesting. So one is the lives led, the books read, the movies watched vary by identity. If I take that identity map, right? So it depends on what you want to take as the null hypothesis, but boy, it'd be really hard to stake a claim that, right? But there hasn't been, but one of the issues, and here's where I think there's a real opening, there hasn't been a lot of work on sort of like looking for differences. Now what has been done suggests that the gender differences aren't as extreme as the racial, ethnic, social class differences, right? In terms of representational diversity, right? But the second thing and Catherine's done a lot of work on this, she's really fascinating. If you put someone in a room of people who are all the same as them, they don't think of as many ideas as if you put someone in a room with people who are different from them. And that's because you're, again, this sort of like, rule of 7 or a couple, we can only think of so many things. So there's a narrowness to how we see the world. And so one of the weaknesses I see in sort of all these terms is I'm sort of saying, here's my perspective. Now the reality is when somebody presents a problem to me, I start generating ways of thinking about it. But if you put me in a more, in a wider space, I'm going to generate more things, right? And there's two things that line up with that people are puzzled over. So one is the bigger the city someone's in, the more productive people are. And if you try and, pull everything out you can, educational, everything else, you still get this residual. And Evan and I were trying to think if the same was true sort of like in terms of like, is the bigger the university are, sort of the more diverse, because you're just exposed to more stuff. And so if you're just exposed to more stuff, you're just going to think of more things, and if you're exposed to different stuff. But what's not true, and this is, I think this verges on sort of like political incorrectness, or just it's an uncomfortable thing to say, but by virtue of your identity alone, some sort of genetic difference, there's no that in and of itself probably isn't going to translate, that this sort of essentialism argument isn't going to translate into different tools, perspectives. Right. I mean, I'm just not, that doesn't make any sense to me, right? But what does make sense is the constructed lives that we lead, right? Very much different. And so then the question is, and so then one of the things, like when we talk about this at NASA a lot, because I spent a lot of time down there, is that it's clear on some problems that those differences are, people will think those are really going to have meaningful implications, right? And then people say, well, maybe on scientific problems, they have less, right? There's people who want to stake that claim. That's an interesting empirical question. And the reason why it's interesting is, you know, you learn a set of stuff, but once the problem becomes really hard, then you start relying on analogy, past experiences, that sort of stuff, right? And when you read, you know, books on innovation and great solutions, it's often, you know, you just think about something in some completely different way. Like there's a great story about the sewing machine, like needles, the hole is at the end, right? So the early sewing machines were horrible because they just got jammed all the time. And Singer was in a museum or something and saw a spear with a hole in the, you know, so the blade, what do you call the head of a spear? Like the blade, the whatever, what is it? Tip. I knew there was some fancy academic word for it. Okay, so there's that it had a hole in the tip. He's like, oh my gosh, if I put the, you know, on a sewing machine, I should have the hole in the tip. You know, so where things come from, you never know. And so I think that you want to have this breadth of experience. But and when I think about places like Michigan, I think that, you know, what we want to avoid is I think you want to avoid completely divorcing the sort of cognitive thing from the identity thing. And I think you want to sort of embrace people for all their differences and try and create a culture of, you know, I mean, it's great that I'm speaking in the EEB department, right? Just, I mean, this sort of interchange I think is great, but it's more the case, I think, that you want to experience difference as something that potentially adds value. So if something says something that, you know, you don't think makes sense, right, to think, oh my gosh, that's a good thing, as opposed to like, you know, but,
You don't agree with me, go
right.
away.
The real problem, though, is that, like, to get here, you had to score high on all those tests, right? So, like, the visiting students are all people who scored high on all those tests. And so, therefore, we think because I scored high on all those tests, right, those things must work, right? But the thing you want to guard against is, like, you know, and this is where the homophily thing is. It's really easy to hire postdocs who went to the same school you went to, who look like you because it's comfortable, right? And there's a real disconnect between comfort and success. If you look at data on, again, another small data set on every single patent ever issued, you see this similar phenomenon. The very best patents are done by people who are using a proximity measure. This is done by my Illinois physicist, Lada Domick, are done by people who are diverse. They've done different stuff in the past. The very worst patents are also done by those same types of people. So, you know, so it's funny. It's like this choice between, like, the homogeneous groups of smart people are B plus A minus land, right? The great stuff and the bad stuff tends to be diverse. Now, you could look at that and say, oh my gosh, we shouldn't be diverse. It's too risky. But what I always like to say, it's kind of like walking or riding a bike, right? The choice is, do we learn to ride the bike, right? And if we can learn to ride the bike, we're going to be getting the things over here. All right, thank you very, very much. I'm happy to stick around and answer questions, or ask questions.